The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI Web Sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Tim Koss will be making our next presentation. Tim has over 35 years of professional experience relating to cementitious materials, concrete, and related applications, including work for the U.S. Army Waterway Experiment Station, Portland Cement Association, the Mississippi Concrete Industries Association, and Holcim. He's a fellow of the American Concrete Institute and active in ACI committees. He was a recipient of the ACI Delmar L. Bloom Award, Service Award in 2010. And he's also active on ASTM committees C1 and C9. Tim Koss is going to talk to us today about some of the synergistic effects of Portland-Limestone cements. Tim? If you want to point it.
Thank you. Many of you may have attended this morning's session on Portland-Limestone cements, and this subject is one that's found quite a bit of interest recently due to some specification changes in the U.S. In the case of this work, I'd like to discuss briefly some of the hydration synergies that may be possible with Portland limestone cements, particularly in combination with supplementary cementitious materials. Synergies that may actually allow us to improve and enhance the performance of concrete. Just as a brief recap, we have quite a bit of experience with Portland limestone cements across the world, around the world, over many years. In the U.S., we have really just in the last 8 years or so seen a minor proportion of Portland cement allowed in ordinary, of limestone allowed in ordinary Portland cement. And then the recent specification changes that I mentioned are common both to ASTM and to ASHTO, allowing a 5 to 15% limestone amount in a blended cement category. And this is something that is some of the cement companies in the U.S. have actually been making the same products for a fair number of years now, for at least 7 or 8 years in some cases. Under ASTM C1157, the performance specification, but the use of these materials has been a little bit limited in the states that rely on ASHTO specifications. As many of the presentations this morning, I'm sure, summarized, there's been quite a bit of literature review from papers published around the world that substantiate the performance of Portland limestone cements as potentially at least equal to ordinary Portland cements in virtually all categories. These are some PCA publications that have done a good job of bringing together many of the literature review on the subject, as well as some new information just recently. As kind of a basic look at what Portland limestone cement is, this is simply the addition of some ground limestone materials along with clinker and gypsum to the finished grinding mills at a cement plant. Virtually any cement plant can do this. This does result in we do grind this product to a higher overall fineness than ordinary Portland cement, and this does slow production a little bit. But what we find is that the limestone portion of this mixture, since the limestone is not as hard as clinker, is more easily ground, the limestone fraction becomes concentrated in the finer particles of the resulting blend. And so the relationship of the particle character of the limestone and that of the clinker becomes a little bit complex because we don't have a direct test method for evaluating that in the finished material. A lot of the literature summarizes that as long as we grind the Portland limestone cement to a level somewhere in the neighborhood of about 100 meters square per kilogram higher in Blaine than the comparative ordinary Portland cement, that the performance is roughly the same. I would argue, and I think I'll show a little bit later in the presentation, that when we do this, we may actually be seeing very fine limestone, but Portland cement clinker particles that are no longer quite as fine as those in the ordinary Portland cement. So this is a very complex relationship. It also follows that if this is true, it may be possible to even extend the performance of this system by grinding a little bit finer yet, and that's part of the subject of this research. One of the interesting things that we find is that the hydration of this material and the synergies that we see are happening both from physical and chemical interactions. Holcim has supplied over 1 million tons of Portland limestone cements in the last few years under C1157. Many of the other cement companies have similar reports of experiences. We've had quite a bit of success with these products and found their attributes to be much as the literature review suggests. Much of the experience has been in the western part of the U.S. where the ASTM C1157 specification has been recognized by some states, and we now have over 100 miles of concrete pavements constructed in the states of Colorado and Utah using this material. This is just an example of some concrete data from our initial experiences with this material that kind of led us to investigate these synergies. And this is 2 different plants represented from 2005, 2006. What we're seeing, even in plants where the response of the ordinary Portland cement with replacement of Class C fly ash was not very stellar, and that was true for both of these plants. When we took the same clinker and made Portland limestone cement, all of a sudden this trend reversed, and we started seeing better behavior, higher strengths at all ages with the same percentage of fly ash replacement. Now, this led us to think that this was something that we should better understand and take advantage of. When you start doing literature review on such synergies, there are quite a number of papers that have been published by authors all around the world on the subjects. Many of them have investigated primarily the setting time influences. It's been found that limestone in the system can be a very useful tool in mitigating the otherwise retardation issues that might be associated with, for example, high volume fly ash mixtures. There are clearly at least 3 different interaction synergies at work that are reported in these papers. These are just a few of the ones that I personally have read. These 3 different mechanisms include 2 that would be in the category of physical phenomenon, that is particle packing and nucleation site phenomenon. But the third is more of a chemical nature. It's actually the formation of new hydration products, carboaluminates that result from the interaction of calcium carbonate and aluminates in the system. And this is particularly interesting from a number of viewpoints as you begin to look at systems with SCMs involved, because some of those systems contribute additional aluminates that can be can combine with the calcium carbonate. And testimony to that is that many of these authors have reported that these synergies and the strength and setting time trends began to improve further as we further increase the available surface area of the limestone. We conducted some initial experiments with laboratory paste to see if we could better understand this. And since the ability to characterize a ground system as far as the distinctive particle size properties of the limestone as it differs from the clinker, since that's very difficult to do, we decided to in the laboratory environment, simulate Portland limestone cement with separate ground limestone additions to ordinary Portland cements. And we did this also in comparison to mill ground Portland limestone cements. And we used some SCM replacement rates that were a little bit higher than norm to kind of exaggerate the trends that we were interested in paste mixtures. Now, these paste mixtures are done primarily because it's a very simple and very rapid way to characterize material performance trends, both with respect to setting and strength. What we do is we actually batch the paste with a kitchen mixer, mix for about 60 seconds, and fill 2x4 cylinder molds with paste. We can do from 3 to 5 dozen of these mixtures in a 3-hour session. And then the next day we come back and look at the thermal profiles to evaluate the setting trends that are occurring, and then we test the 2x4 cylinders in a compression machine for strength trends at the ages of interest. Using this technique, we began to explore these properties with simulations of Portland limestone cement, and I've got a couple of hundreds of different data points. I've tried to dumb this down to just a few to show some trends. But this is a trend that we see with ordinary Portland cement, no SCMs involved at all, with simulations of 10% limestone cement. And we varied the fineness of the limestone to better understand the influences there, all the way from a fairly coarse limestone, significantly coarser than the cement that we're using, to a very fine limestone that we frankly thought was probably in the neighborhood of what the Portland limestone cement system was actually, if you could delineate the limestone. And here's the performance: 1 and 7 day paste strengths. I don't have 28-day data on this, unfortunately, for this paste without any limestone replacement of the cement. And this is the axis for the thermal setting times that we observed, which are indicated with the diamonds. And as you can see, when you go to 10% limestone replacement with the coarse limestone, the strength performance is detracted initially until you begin to make that limestone finer. And at a certain point, you can actually essentially recapture the lost strength from the 10% dilution of Portland cement. The setting times also become quite interesting because the setting times begin to get faster with the finer limestone. Nothing else has changed in these systems. Now, the interesting thing is what happens when you do this same work with SCM replacements as we would use in concrete. Here is the same comparisons for a 40% replacement using a Class C fly ash, which is a high calcium Class C ash that contains a fairly significant aluminate contribution. And this type of fly ash results in significant retardation anyway. The numbers on the time scale for setting are different here, the much longer setting times. And as you go to the coarse limestone replacement at 10% of cement, then you begin to see even more retardation. But that retardation is mitigated as you go to the finer limestones. Notice the strength trends, both early and both 1 and 7 day strengths. Very interesting strength enhancement as we get the limestone finer and finer. We believe this to be associated with the aluminate interaction with the calcium carbonate. Class F fly ash is a little bit less interesting with respect to strength, but you do see the enhanced setting times similar to the ordinary Portland cement alone. Later on, we included some slag cements in some different studies, and we were also interested to see what the effects of not only 10% limestone systems, but up to 15%, what that would be. And here is a similar mixture, a simulated mixture with 10% limestone of the finer grind that we had played with before, with 40% no SCM, 40% C ash, 40% F ash, and 40% slag. Now, here's I'm sorry, this is without the limestone. This is with the 10% limestone as we had done before, and this is at 15% limestone. And you can see that even at 15% limestone, in general, we're at least equal to, and in many cases, outperforming the system without limestone included. Now, what was particularly interesting to me is when we took these sets of mixtures with 10% limestone of the finer grind that we had played with in the laboratory. We repeated this work with those same proportions and compared that to the performance of cements, mill ground Portland limestone cements from our cement plant at the 10% level, theoretically the same material as we were attempting to simulate. The interesting thing is, and here's the system of the laboratory separately proportioned paste mixtures. Here is a 10% mill ground Portland limestone cement at about 500 meters square per kilogram Blaine. And here is a slightly finer, about a 550 meters square per kilogram Blaine limestone. Presumably similar clinkers, not the same clinker sample because the mill ground systems collected on different days. But you see that the mill ground samples significantly outperformed the laboratory simulation that we had been doing before. And so this told us they outperformed both in strength and in retardation mitigation. So this led us to believe that our initial estimates of the fineness of the limestone fraction were probably not very good, and we're actually much finer than that in the limestone system. When you read the literature on the relative fineness of these materials as they might be resulting from a mill ground system, this is one of and there's a citation you can read in the handout there on the bottom. This is a graph that appears in one of those references that depicts the cumulative mass distribution of particle sizes for both the composite cement, which is in red, the clinker in green, and the limestone in blue. And based on this general, and we knew this to be roughly true, but what this is telling us is that as you get into the smaller and smaller particles, they become more and more limestone concentrated. We then took the different materials that we had been using in the laboratory, both the separately proportioned materials as well as the Portland limestone cement ground in the mill, and we did a particle size distribution analysis of these materials and actually proportioned in an Excel spreadsheet what they would be for the separate components that we had batched in the laboratory. The ordinary Portland cement is in blue. This is about 76 microns. This is about half a micron in here to give you an idea of where you are on the chart here. The blue is ordinary Portland cement. The red is the resulting combination of 90% Portland cement, 10% ground limestone, and the green is the actual mill ground system at 500 meters square per kilogram. So you can see that we were indeed missing the concentration, I should say, of the very fine particles that are much more prevalent in the mill ground system. So what does this mean in the grand scheme? Well, we think this is kind of a shoot from the hip depiction of what's going on as we increase the grinding time in the mill. This is kind of an educated guess. We've not been able to come up with a good test method for evaluating the different proportions of the finished product. But if this is roughly true, then here would be a couple of examples about the fineness of the different materials that we're actually, that the component materials of the Portland limestone cement. As the Blaine of the PLC increases, the Blaine of the clinker is increasing very slowly, but the Blaine of the limestone is increasing much more rapidly. Here would be an example of about 100 meters square per kilogram higher than the ordinary Portland cement Blaine. Okay, if you only go up another 50 points, you see the additional limestone fineness is significant, but the additional clinker fineness, we're probably not even back to the original OPC fineness of the clinker particles yet. That's our premise anyway. That's where we think we are with this. So in conclusion, most of these conclusions are fairly obvious. I think I won't read them to you. This is available on the website if you'd like to take a look. We're doing additional research, trying to better understand these relationships and better characterize the material in a Portland limestone cement that's been ground in a finish mill. One of the things I'd point out that's kind of a stumbling block for us in the industry as we're trying to do the education and promote this material, particularly with DOTs, is that because of the specification category for Portland limestone cements under the new blended cement spec, many DOTs will consider that when you add a fly ash or slag cement, or certainly silica fume, anything else like that, to this system, you now have what they refer to as a ternary system, because the limestone is considered part of the cementitious components as a blended cement. And ternary systems may not be allowed in their specifications. So now we have a caveat to work through. If we're going to derive the benefits from this synergy, we must be able to use supplementary cementitious materials with Portland limestone cements, just as we would with ordinary Portland cements. And it might also be possible, as this work begins to suggest, that we might even further enhance sustainability, not just from the limestone component of the cement itself, but maybe even by increasing the percentage or the replacement rate of supplementary cementitious materials. So that's where we are. We'll continue to work on this. There's some other research that's beginning by other researchers and universities as we speak that hopes to develop additional information, including things we might be able to do to cement chemistry to better capture these synergies of hydration. I thank you for your attention.
Thank you very much, Tim.